Okay, so last time we have talked about prime avoidance and Chinese remainder theorem. So what today I'm going to discuss is that I will state some facts about Coulomb ideals, etc. And then we will do some exercises to see how all these things what I have been talking about since the last 3 lectures, how they are applied to some cases. Okay, so I will start with Coulomb ideals. So suppose A is as before commutative ring with unity. Suppose alpha and beta are ideals of A. Then I am defining some quotient of ideals, and that is defined as all those elements X in A such that X beta is a subset of alpha. And it is easy to verify that this is an ideal. Now, why is that an ideal? Because if you take X and Y, then X plus Y times beta is X beta plus Y beta is contained in alpha. And if you take X and if you multiply with some ring element R, let's say, then R times X beta is in R times alpha, and hence it is in alpha. So this is an ideal. Now, why this thing is necessary? This will have some role in case of primary decomposition, etc. But we will see some trivial facts about these things today. Okay. So, for example, if you take 0 colon B, so I am writing down it's a remark, then you see that is set of all X such that X when multiplied with any element of beta becomes 0. So that means this is named as annihilator of beta. So annihilator of beta is the set of all elements X such that X times any element of beta goes to 0. Also, if I write down the set of all 0 divisors in this notation, then that is union of annihilators of X where X runs over non-zero elements. And therefore, this becomes union of 0 colon X where X runs over non-zero elements. Now, 0 colon X, by this notation, I mean 0 colon ideal generated by X. So this will be my convention. Okay. So I am going to state some properties of it. Maybe I'm going to give you an example. So example, suppose A is the ring of integers, alpha is an ideal generated by M, and beta is an ideal generated by N. And also suppose M is product of P to the power some UP, P is a prime and it's a finite product, and N is product of P to the power VP. Again, P is prime finite product, this is just prime decomposition. Then what is alpha is to beta? Now I'm claiming that alpha is to beta. So you see, you need to multiply n times something so that it becomes a multiple of m. So therefore you have to add the extra prime factors there, nothing else you need. So you take and this is an ideal of Z, so it has to be principal. So you take Q to be some product of P times gamma P. P is a prime and it's a finite product where this gamma P is, you take maximum of UP minus VP comma 0, and that is what UP minus minimum of UP comma VP. So that's what you are taking, and then if you multiply with that, if you multiply n with this thing, then the product will have all the prime factors greater than u, and thus this hypothesis will be satisfied. So therefore q becomes m by GCD mn, which is the same as LCM of mn. Okay, so now I'm going to state some properties of it. Properties. So first of all, if you have some ideal alpha and if you take A, then the colon ideal become the ideal alpha itself. The colon ideal becomes alpha itself, because if you take some element x from alpha and multiply with A, then it resides in alpha, and conversely, if you have some x in the colon ideal, then see x times 1, that has to be inside alpha, and therefore x is in alpha. So this is a trivial observation. Now if you take two ideals alpha beta, then and if you achieved that alpha beta, this colon ideal is A, that happens if and only if your beta is contained in alpha. So that is because first of all, if suppose one implication holds, this alpha is to beta equals to A, and you need to show that your beta is a subset of alpha. So you multiply an element of beta with 1, because the colon ideal is A, so 1 is there. Then this x is inside alpha, and therefore your beta is a subset of alpha. So one part is done. And for the other part, if your beta is subset of alpha, then multiply beta with anything of A, then it will be inside beta and hence inside alpha. So the second one is also trivial. The third one says, if you have three ideals and if you take colon of alpha and beta and then gamma, then this becomes colon of alpha and beta gamma, which is same as colon of alpha and gamma then beta. So I'm proving them one by one verbally. So suppose I have taken some x from here. So suppose x is here, then x times gamma is inside the colon ideal of alpha and beta. That means x times gamma times beta is in alpha. And gamma times beta, you can write it as beta times gamma, product of ideal, and they are commutative. Therefore, x times beta gamma is inside alpha, therefore x is here also. So this implication is done. Now the converse part. So if you take some x from here, then x times beta gamma is inside alpha, and therefore you can again change it. So x times gamma times beta is inside alpha. So if you multiply x with gamma and then multiply it with beta, then it becomes inside alpha. Therefore x times gamma is inside alpha is to beta. Therefore x is inside the colon ideal of alpha is to beta colon gamma. So this inclusion is also done, and therefore they are equal. Now for the third part, you see that this thing is commutative. So you can write alpha is to beta gamma as alpha is to gamma beta, and then this follows from the first property, and therefore part 3 is also done. Okay, what is next? So fourth one is that if you have some inclusion kind of relation, beta subset of gamma, then that implies alpha is to gamma subset of alpha is to beta. Because if you take some x from alpha is to gamma, then x gamma is inside alpha. And if you multiply the same x with beta, then x beta is inside x gamma and therefore inside alpha. So this was again a trivial statement. Okay, now therefore, so in particular from this, what you can say is that you have always for any ideal alpha is subset of A. That implies alpha is to A is subset of alpha is to alpha. maybe no, what I'm trying to say is that beta is a subset of A, then alpha is to A is subset of alpha is to beta for any ideal alpha by the previous thing. And this is alpha, and therefore what you get is that alpha is a subset of alpha is to beta every time. But anyway, this is I mean, this you can see directly. Okay, so this one is also done. Next property is that you take alpha is to beta and multiply it with beta, then it resides inside alpha, and that is just direct from the definition. That was the definition of alpha is to beta. We want to achieve this thing only, and alpha is to beta is the largest set of elements which helps you to achieve this property 6. Okay, now some sort of associativity property is there. Okay, so we have discussed the associativity property. Some sort of distributivity kind of things are there. You take intersection alpha is to beta, then it becomes intersection of alpha is to beta. That is because if you take x from intersection alpha is to beta, then x beta is inside intersection alpha, therefore it is inside every alpha, and therefore x is in the intersection of all these coloridials alpha is to beta. Now if you take x from intersection of the coloridials alpha is to beta, then that means x is everywhere, and therefore x times beta is inside alpha I for every I, and therefore it's in the intersection, and therefore the other inclusion is also over. And finally, we have, if you take alpha is to addition of beta j, then it becomes intersection of alpha times beta j. Alpha is to beta j. So take some x from addition of beta j, from alpha is to addition of beta j, then if you multiply it with any element of beta j, that is an element of the sum, and therefore it becomes inside alpha, and therefore x is in alpha is to beta j for all j. So x is in the intersection, and now if x is in the intersection, then x time any element of beta j is inside alpha, and if you take the sum, then it's a finite sum of elements of beta j, and therefore multiplying x with each of them takes this inside alpha, and therefore you are done. So all the properties are over. Okay, so having said colonidials, what I'll say next, again, all these facts are sort of looks like they are discrete kind of facts, but we will unify them together later on with more developments in our study. Now we are going to extend our definition of radical to arbitrary subsets, and we will prove 2-3 statements about radicals before moving to extension and contraction. So what in this lecture I am planning to do is that I am planning to complete this chapter 1 of Atiyah, and then once that is done, what I will do is that I will discuss some exercises. I will show some further properties of rings, etc. And then we will be introducing the Zariski topology, both on rings and both on Kn, that is affine space. And from there, what we will discuss is that I am planning to head towards a simple proof of Hilbert's-Null stanzas before moving to some more amount of or some dedicated amount of study of module theory. So we will be planning in that direction right now. Okay, we will be going to that direction. Okay, so define for a subset of A. So suppose E is a subset of the ring A. Define radical of E as the set of all x in A such that x to the power n belongs to E for some n in natural number. But for an arbitrary subset, what we cannot say is that this radical is an ideal. So that may not be true in general. So For an arbitrary subset, radical A may not be an ideal. Okay. But also we will have properties like this. So observation that if you take union of E alpha, radical of union of E alpha, then you will get this thing, because if your x is in radical of union E alpha, then x power something is in union E alpha, therefore something is inside some E alpha, and therefore x is in the union of radical E alpha. And conversely, if you take x from union of radical E alpha, then x is in some radical E alpha, therefore x power something is in E alpha, and therefore in the union. So you are done in that way. Okay. So having defined that, what I'm now going to prove is that proposition, if I denote the set of zero divisors by D, then D turns out to be union of radical annihilators of x non-zero. So you see that annihilator of x is an idea, because it was defined in that way. You take all the elements a such that a times x becomes 0, and this is clearly an idea. And if you take the Coulomb ideal notation, then there also it is clear, because this is the Coulomb ideal of 0 and principal ideal generated by x. So what we will show is that this zero divisor set is the union of these radicals. Okay, so for that, let's prove it. So first of all, I need to check that D equals to radical of D. Now, why is that true? It is clear that D is subset of radical of D. See, the definition of radical over arbitrary subsets also have the same property that E is subset of radical of E for every subset E. And so D is subset of radical of D. Now, if you take some x from radical of D, then x power n is inside D. You take the smallest such n, and then there exists some non-zero y such that x to the power n y is in x to the power n y is 0, and this n was smallest, and therefore if you take x to the power n minus 1, then that times y cannot be 0, so that is non-zero. That makes x to be a zero divisor. And therefore if x is in radical of D, then x is in D. Now what was D? D was union of, so I have written down zero divisors here. This was union of annihilators of x. So this is radical of union of annihilators of x, where x runs over non-zero elements. Now we have seen some property of radical over union. So you can take this union out. So it becomes union of radical annihilator of x. And that's what we wanted. And thus our proof is done. Okay. So having done that, I am going to show you another example. In fact, I am going to give you this as an exercise. If you take the ring Z, and if you take your ideal to be generated by some M, and suppose M is P1 power alpha 1 up to Pk power alpha k, where all these Pi's are distinct primes, then just check that radical of A will be the ideal generated by P1 up to Pk. Also, since we are talking about radicals, therefore I am going to give you another proposition which says that if you're, so we have seen earlier that if your ideals are co-prime, so maybe I'm writing down it. So observe that if your two ideals are co-prime or co-maximal, then what happens? Alpha plus beta is 1, but then radical of 1 is what? It is 1, and that means radical of radical alpha plus radical beta. We have seen earlier in some earlier lecture that radical of alpha plus beta becomes radical of radical alpha plus radical beta. So maybe, so we have this result in general, right? Radical of alpha plus beta is radical alpha plus radical beta. Now let's examine what happens if alpha plus beta is 1. then this left hand side becomes A, and therefore this right hand side becomes A, and therefore this so also we had that result that radical of A is 1 if and only that is the whole ring. So this becomes A. So what you get is that if your alpha and beta are coprime, then radical alpha and radical beta will also be coprime. Now what I am proving here is the converse. That if radical alpha, radical beta are coprime, then alpha and beta will also be coprime. And that is again by the same relation. So you have, the proof is very simple. You have A to be equals to radical of radical alpha plus radical beta, because radical alpha plus radical beta is A. So its radical is again A. And this is radical of alpha plus beta, but that implies alpha plus beta equals to A, and you are done. Okay. So you are done with all these simpler facts about radicals and colloidials, etc. Okay, maybe for now I am not going to the extension and contraction part. I will be coming to that later when I will describe Zariski topology. Although the exercises I am going to discuss is not in a linear fashion, so I'm not discussing the exercises just maintaining its order. I will discuss it as I think it is suitable, and therefore we are going to do some things. And as of now, I am just postponing the discussion on polynomial rings, and I will be discussing them in detail maybe 1 or 2 lectures later, because we will be needed those things, and we want to prove the Hilbert-Null strangeness. We want to give you a proof of simpler proof of Hilbert-Null strangeness. So I need to develop some machinery for that. That will be done systematically sometimes some moment later. And therefore, just today we are going to discuss, for the rest of the class, we are going to discuss some of the exercises from various sources, including Atiyah MacDonald, to show you how all these things are used in practice. Okay, so here are some exercises tutorial. Okay, so the first problem is that suppose x is a nil radical of A, then 1 plus x is a unit of A, and hence your nil radical of A plus nil radical of A plus A star is a subset of A star. So that's what I am going to prove. So that is see, that is obvious, because if your x to the power n is 0 for some x, you for a motivation you should look into the formal power series expression of 1 by 1 minus x, or maybe you can, for your motivation, you can think it as x is a real number whose absolute value is less than 1. Then what do you get? 1 plus x square up to this geometric series sums into 1 by 1 minus x. So if at some point formally now you think, if at some point this x to the power n becomes 0, then you get a finite sum and therefore a ring element, and if you multiply it with 1 minus x, this gives you 1. So we are going to use that idea. So you see, some x power n is 0, so you can also say that minus x is also nilpotent, because nil radical is an ideal. And thus I am going to prove this for 1 minus x. For x, you take x to be equals to minus y and prove it for minus y. Okay. So what I am proving is that 1 minus x belongs to A star. This is what I am going to prove. And that is simple, because if you take 1 plus x square up to x power n minus 1, then you see that this turns out to be telescopically this, and this is equals to 1. And thus you are done. And for the next part, that nil radical plus units of A is inside units of A. So you take some element of nil radical, let's say x, and u from units, and then you take this u common, then u plus u taken outside, 1 plus u inverse x. U inverse x is also an important element. By the previous thing, 1 plus u inverse x is a unit in A, multiplied with u, it still is a unit in A. So you are done with this exercise. Okay, good. Now, now what I am giving you as an exercise is that if you have two ideals, ideal generated by M and ideal generated by N, ideals of Z, just try to compute what is your this is your alpha, this is your beta. What is your alpha plus beta? What is alpha intersection beta? What is alpha beta, and what is alpha is to beta? And find them in terms of M, N, their GCD, their LCM, etc. This is a very much I mean connected exercise for your basic undergraduate or maybe school level number theory knowledge. So you will see that what you learned there will be used here. Okay. Okay. So the next exercise will be, next what I am going to prove is that so you see the exercises are, these are purely just kind of discussions, and they are not in a well organized order, but okay, fine. You will be using them sometimes, and therefore you will be more comfortable with them. So okay, what I am going to prove is that now every prime ideal, so my statement is that every P in spec A contains minimal prime ideal. In particular, your ring has a minimal prime ideal. Minimal prime ideal means what? That you have a prime ideal and no proper subset of that cannot be a prime ideal. Can be a prime ideal. Okay. So that is what I'm going to prove. So for the proof, again, this is a typical John's lemma argument, and this exercise shows you that John's lemma is quite frequently used in the study of commutative algebra. And how do you formulate such statements? Okay, so I need to show that every prime ideal contains a minimal prime ideal. Therefore, I need to first of all get a set which is partially ordered, etc. And then we will do some inclusion, etc. ordering that will be there, and then we will get some upper bound for a given totally bounded subset, and hence by John's lemma we will get a maximal element. Okay, now the thing is I'm talking about maximal element, but we are trying to find minimal prime ideal. Then how do I connect this to sort of things in the opposite poles? So John's lemma give you maximal elements, but John's lemma does not specify what the ordering should be. So your minimal prime ideal in terms of inclusion, if you want to find minimal prime ideal, then you try to apply John's lemma using maximality on reverse inclusion. So I am taking this collection of all the prime ideals Q, all the prime ideals Q, such that Q is contained in P, and I am defining that I less than equals to J in C if J is a subset of I. So I am doing the reverse sort of inclusion here. Then you see that first of all C is non-empty because your P is already a prime ideal which is contained in P, and therefore if you take a chain, so you take a chain like this, chain in C, then if you take the, so there you in case of finding out maximal ideals, we were taking the union because that was a direct inclusion. Now for the reverse inclusion, what you expect that it should be the intersection. So define I to be the intersection of I alpha. Now this is an ideal because intersection of ideals is an ideal, but I don't know whether it is prime or not. So suppose xy does not belong to your I, and see all these I alphas are prime ideal. So x and y does not belong to I. That implies that there exist alpha and beta such that x does not belong to alpha, I alpha, y does not belong to I beta. But some either I alpha is contained in I beta or I beta is contained in I alpha. Now suppose suppose I alpha is contained inside I beta, and your x is not in I alpha, y is not in I beta, so y can neither be inside I alpha also, right? So therefore there exists gamma. So I am taking this in the example I was talking about, I am taking gamma to be alpha. So there exists gamma such that xy does not belong to I gamma, but I gamma is a prime ideal, therefore xy cannot belong to I gamma, therefore xy cannot belong to I, and thus making I to be a prime ideal. And that I is contained in P, that is a trivial statement because all these I alphas are contained in P, therefore their intersection will be also contained in P. And thus by John's lemma, there exists a maximal element. Remember, I am writing maximal element here of C. But remember, maximal element of C by definition of C and the partial order becomes a minimal prime ideal of A. Say what? Say this grothic P. Then by definition of C and this ordering, this turns out to be a minimal prime ideal of A containing P, contained in P. And that completes our proof. So these are typical John's lemma kind of arguments. So maybe sometimes I will say that by John's lemma this happens, then all these kind of arguments are embedded inside that. Okay. Okay. So next problem what I am going to do is that suppose A is a ring and so suppose A is a ring and I is an ideal. For okay, so what I'm trying to say is that for every ideal I of A not contained in nil radical contains a non-zero idempotent. Now, what is an idempotent? Idempotent is an element E such that E square equals to E. So if you take the multiplication with itself, it will give you the same thing in return. And non-zero means that E cannot be zero. Okay. So prove that this nil radical of A is same as Jacobson radical of A. This is what we want to prove. Okay. So first of all, we have one characterization. Nil radical of A is the intersection of prime ideals. Jacobson radical of A is the intersection of maximal ideals. Now, if you take in maximal ideals are prime, and if you take intersection of all the prime ideals, then in particular all the maximal ideals are there, and therefore this is contained in the intersection of all the maximal ideals. So anyway, this is true in general that nil radical of A is contained in Jacobson radical of A. This does not require any hypothesis. This is for any ring. This is true. So we need to prove the converse part. Okay. So we have done one characterization on Jacobson radicals also. But we have seen that X belongs to Jacobson radical if and only for every Y, your 1 plus XY is a unit. So suppose X belongs to Jacobson radical. Therefore, we know that 1 plus xy is unit for all y in A. We want to show that x is in the nil radical. Now, what happens if x is not in the nil radical? If x does not belong to nil radical of A, that means by the hypothesis, x, this ideal generated by x contains contains a non-zero idempotent. So you have some y such that xy square is equals to xy. Okay. So that means what? That means this xy times 1 minus xy is equal to 0. But because this is just, you take the whole thing to the one side. Okay. Now, by the hypothesis, this 1 plus xy was a unit. Therefore, 1 minus xy is also a unit for every y that was true. And that will imply that xy is 0. But xy was chosen to be a non-zero idempotent. So that is a contradiction. And therefore, x has to belong to nil A. And this completes the discussion of the proof. Now we are going to discuss a similar kind of problem. So this that was problem 3, and next one is problem 4. So suppose A be a ring, and for all x in A, you have this x to the power n equals to x for some n. So this n is not fixed for all x. This n varies over x, but at least you know that some power of x will be x itself. Then show that every prime ideal is maximal ideal. So you need to show that set of all prime ideals is same as the set of all maximal ideals, and one side is clear always, like maximal spectrum is always contained in prime spectrum, and therefore we need to show that given any prime ideal that gives a maximal ideal. So let's see how to prove it. So suppose P is a prime ideal, then what we know? We know that A mod P is an integral domain. So I need to prove that A mod P is a field. So take some x from A mod P, x non-zero, means x bar non-zero. That means x is not in P. Okay. Then you know that there exists n such that this x to the power n becomes x, and therefore going modulo P you get to x bar. Take everything to the same side. So you get x taken common, -1 is equal to 0. But that means since A mod P is a integral domain, this is 0 and x bar was non-zero because A mod P is integral domain. And that means x bar to the power n minus 1 equals to 1. Now, if your n is greater than 1, then you are done. If your n is greater than 2, I'm sorry, if your n is greater than 2, then this is, there at least 2 x bars are there, and therefore x bar times whatever x bar to the power n minus 2 is equal to 1, and you are done. If n is 1, okay, sorry, if n is 2, because our hypothesis started from n greater than n equals to 2. So if n is 2, then x power to the power 2 minus 1, x power 1, that is x bar, is 1. Therefore, it is already a unit. So this proves that A mod P is a field. and thus P is a maximal ideal. So this was a very trivial. Okay, so we have discussed some propositions, some properties today, and then we have discussed some little bit of problems which one should try on their own to just get some hands-on practice on the subject. However, so next what we are going to do is that next day we'll also devote it to some discussion on problems, and then we will introduce the Zariski topology maybe on the next day or maybe on the lecture after that. So okay, I am going to stop this lecture here. Thank you.